Let's get back to our ordinary differential equations. So quiz question number 1. Will I, in this course, ask you to find analytical solutions of differential equations, which I know is your favorite topic from then 437 J. I rolled. Will I ask you for analytical solutions? No, that you keep in that other course. Here, I'm going to basically ask you for numerical solution, which applies in cases where you don't have analytical solution. Well, it applies all the time, but basically this is for the majority of the cases for differential equations out there where we don't have analytical solutions. Analytical solutions are very important, and they exist. However, they exist for a very limited class of differential equations. They have to be linear, this and that. So it's actually a very narrow class. In most of the realistic applications, the equations will be more complex, and we need a numerical way to find the solutions. So we introduced the simplest method. So basically what it comes down to is as follows. If I have an ordinary differential equation, so I'm looking for function y of x, such as that the slope dy dx is given as some function of both x and that function y. Okay, so this is a generic form for this differential equation. Then the simplest thing I can do is as follows. I will start from a point that I know. So that's my initial value. These are initial value problems. And that point, xi, yi, so that point has a value xi that I refer to as xi. This is my previous or a starting point. And it has a value yi that I have either given as an initial condition or I already computed somehow in this iteration. So if I have that starting point, then my next point, I'm looking for values, what is my y at certain values of x. So when I'm looking for a numerical solution, I will not get a closed formula for that solution. I'm really looking for values of that function y at certain discrete points. That's how I numerically solve problems. Okay, so I cannot get a formula. For that, I go to a different course. Here, I'm looking for a numerical solution. So this value of the function y at this next point, xi plus 1, is given as my previous value plus some slope times h. And this is essentially motivated by Taylor's formula. This is Taylor's formula with all of these higher order terms like h squared and so forth chopped off, where h is difference, it's a step size in x points. Okay, so let's look at that on the graph. So this is my xi, this is my yi, this distance here. So this is the point. This is this function that I'm looking for that I don't know. But the best I can do is estimate my value of this function, which is in this case here. I want to estimate this value at this next point xi plus 1. And the way I'm going to do that with what we call as Euler's method, the simplest one, is I'm just going to take the slope, which is dy dx, which is essentially given by f of xy. Okay? So this slope phi in the simplest case is simply f of xiyi. It's the value of this slope that is actually given by the equation. So that's the simplest I can do. So this is essentially a formula. On a certain level, at this point, when you see a formula like this, you should be starting to write a for loop already. That's how I figure this out. All right. So on a certain level, even if you don't understand the formula, you should be able to do the mechanics of simply programming. But the understanding is simply that basically this is my simplest, so h is my step size, it's this difference here between my x values. X values I decide on myself based on the problem. and then I'm looking for this values y of the function. So this is not, unlike in finding the root, where I'm looking for one point, I'm here actually looking for an array of points. So this is going to be array of x's, an array of corresponding y's, which give me value of the function I'm looking for at those x's. Okay. So I'm going to get an array as a result, not just one root, the way we did in Newton-Raphson method. Okay. So that's the difference. So I'm basically stepping in space. This is not iteration on one point. I'm actually stepping in space and getting my values of function y, or estimates of them. Okay. So essentially, this is how it would look like when it's actually kind of pretty bad. So this is my true solution, but here I started from this point and the slope was pretty steep and I took it too far. My h was pretty large. So if my h is 0.5 here, I'm going to kind of go too far, and the difference between the estimate and the true solution is pretty bad. Okay? And that's an error that I made. And then I'm taking that into the next case. In next case, again, I estimate the slope at this point and take it for 0.5. So now I have the error that I made previously plus the new error that I'm making, right? And that's what basically gets me pretty far away. However, as I reduce h, I reduce my error as well. So if I didn't go this far here, I went only halfway, my error would be smaller as well. So typically, I always improve with making h smaller. And I can actually analyze that. We mentioned this last time, so I'm not going to go into detail, but basically, since I got this idea from chopping off higher order terms in Taylor's formula, that's basically how I can see that the difference, this is my error, and it's going to get smaller with smaller h, because if I have h of 0.01, 0.01 square, which is the leading term here, is smaller as the h gets smaller. So this entire thing gets smaller as h gets smaller. So I get better. Excellent. So basically this is, with smaller h, this is how I would get closer to the true solution. So let's try out pretty much this. This is actually a simple exercise. So we started doing this by hand last time, and today we're going to program. So we're going to consider a simple differential equation, and actually the one that I can easily integrate. I'm not asking you to integrate, I actually gave you the solution, but this one you should be able, if I wake you up at 2 a.m., you should be able to integrate that one, because it doesn't have y anywhere. It only has x's, right? So I just multiply by dx and integrate, right? And if I integrate, I'm going to get the solution y of x. And that's actually given here in the next line. Okay? So I have an analytical solution so I can check how well I'm doing. That's the whole point in these problems where I have an analytical solution. So we're going to solve this with this Euler's method. This is Euler's method formula. And we're going to solve it on interval from 0 to 4 with step size h is equal to 0.5. And so my starting point, initial point that I'm starting from is 0, 1. So it has a y value of 1 for corresponding x's. And we computed last time the first step solution using this formula. So if I plug in x0 and y0 into this formula, I'm going to get my next y. Great. And I also have analytical solutions, so I can figure out what my relative error is with respect to the true solution. Now I want you to program this. So I want you to create a function, Euler method, and that function will take h as an input. It will take x0 starting point, y0, so x0, y0 is my initial point that I'm starting from. And then what is my interval end? I can go for x until 3, 4, 5. Here I'm asking for 4, but I want that to be input of the function. Okay? So I can change it as I want to. And what this function is going to give back is going to return x and y, which are x's and corresponding y's. That's essentially my solution y of x. I have x's and corresponding y's. And that's how I'm solving this problem numerically. And then I want you to compare the solution. Since this is a function that can take any h, I'd like you to vary h and see if indeed you get better with smaller h. So we're going to try it for 0.5, which is what I actually shown on the slide, 0.1 and 0.05, and compare that to analytical solution as well. So we have our work cut out for us. Let's get going. So basically, I'm just reading right now. I'm going to start you off. It's a function Euler method. What is input? Read the slide. Okay, so all of these are input. So my h, spacing, my starting point x0, y0, and my interval end. So I'm going to execute this with interval end of 4, but right now I'm still leaving it as an input to the function so I can change it, right? And what is this function going to return? X and y, which are arrays, right? So if I'm supposed to start at x0 and end as xn, and I have a spacing of h, how do I create my array of x's? So linspace or range or anything in between that will give you a equally spaced array, right?
And if we can put the step at the end.
So linspace, yes. So with a range you can do step. Okay? But you can make linspace work. So either of those will work. Okay? So what I'm going to put here is that's the simplest thing you can always do is create your space of x's. So first things first, I need to import numpy as np. So my x is x0, xn, and I'm going to just make it a little larger. Remember that arrange business? So if nothing, at least I have x. So, okay. So what I've so far put down is just certain mechanics of solving a problem that you should at this point just be able to put down on a paper regardless of even understanding which method you're. And that mechanics kind of gets you going, and it's important actually. So write down what you know always. And then my y is an array of corresponding values to x. Therefore, it has to have the same size. So in terms of mechanics of solving the problem, well, let me just give myself zeros of the same shape. So at least I've reserved memory for it. Excellent. So now it's on you to actually program the rest of this. So first starting point you have, that's x0, y0. You make sure that it's set correctly. And once you do that, then I want you to step through all of the others and solve this problem. And please do so, so define yourself a function f of x separately. X, it's f of x here, okay? But I'm gonna make it more general, f of xy, so we can easily reuse this function for a different one, okay? And return. So then if you're solving a different problem, you can quickly change this f and run with it, right? Alright, so I started you off. Ningyo and I are walking around helping out. And I did post the slides if you want the slides. Trying to negotiate space here for both. There we go. So that's my endpoint until which I go. So I say this is 4 in this case. I say solve Euler's method from 0 to 4. So I start from 0. All I know by this formula is how to get to the next point that is h away. But I gotta stop somewhere. I can't just keep going. So I stop at 4. So that's so I'm gonna solve for 0, 0.5, 1, 1.5, 2, 2.5, 3, 3.5, and 4. So I gotta solve on an interval, otherwise computers don't do infinity. Slides are on canvas if you can't see properly. Doesn't matter, that's up to you. But this, the meat of the function, this is just kind of help out. Now how do I program? So what I need to program is that f in general, yi plus 1. So my next y is yi, which is my previous y, plus f of x on yi times h. And I need to walk, so all I know is this initial x0, y0. That's what I'm starting from. Any next one in this, so here I just kind of gave this, I know what x's are, but y's I have to come up with. So I gotta walk through all of them and set them based on that formula. How do I walk through all of the y's? What load do I need? That's your f of x. That's what you're solving. dy dx. This is another equation. Check against these.
So the formula.
This is what you're solving. dy dx.
So this goes in the half.
Yes. So again, you're solving this part here. dy dx equals to minus 2x cubed plus 12x squared minus 20x plus 8.5. That's what I threw in here as an f of xy. That's your f of xy. Okay? So that's in here. And now this is how you're going to solve it. This is your solution for every y. So you got to walk through all of the y values. Whoa! Whoops, sorry. And set them based on this formula. And there's a specific loop that does that. And never forget to initialize.
So while loop.
Either can work. For loop is a natural for this one. You can make while loop work. But you know how many you have. This is how many you have. They're all in this. Right? So first things first, do not forget to start them off with x0 and y0. So that's your initial point you're starting from. And then x's you already have, well, x is already given, so this is not necessary because that's how we created x. But this is necessary. And now all the other y's I have given by this formula. I gotta walk through them and set them. How many? Gotta figure out how many. How do I get this number of elements in a vector, length of a vector? Any suggestion? However many I have in x. How do I find out? I don't know. Okay, so now I know how many. Great. Now what? Start the for loop. And I can start from the number 1, right? Or actually, nah, this is fine. If I'm following this formula, then if I start I as 0, then my I plus 1 will be the next one, right? So what do I write here? I'm following the formula. I'm just typing it in. What's H? It's H. It's given. It's an input. I have it.
We don't need iters then?
Hmm?
We don't need to put
This is it. It's a one-liner, essentially. So the meat of the problem is, so this is that slope, okay, which in this case is simple. It's given by dy dx is f of xf. So all I did is translated the formula that is on the slide to what I have. I have an array x, array y, so I gotta do x of y, y of y, right? And then the only thing that I gotta worry about here is this last one. If I try to go to n and I don't have enough to have n plus 1. Okay, so all I'm gonna do is do this. Since my formula kind of works with the next one, so I just have to be careful. If not, well, it's gonna yell at me, so I'm gonna go and fix it afterwards, right? That's it. So key thing is in every method, I gotta initialize my points, right? And I gotta give myself, this is arrays, so I'm returning arrays. I gotta allocate memory for that. X is, I decide X, I discretize my space of X's. And in this case, so we're gonna now call this for 0 and 4 on that interval. So now I gotta, to actually see whether this works, I gotta call the function. And what I'm gonna say is xy, that's what the function returns, is Euler method h of 0.5, starting 0.01 and ending 0.4. So that's this xn is my interval, end of the interval 4. Yes? And hope that I get the result. Let's see. I got something. So, but I can print x, I can print y. My x is, well, correct, but it should be. It's values from 0 to 4, spaced 0.5. That's what I asked for, right? And my values of y, they start at 1, well, they end at something. I don't know whether it's correct. How do I find out if it's correct? I have analytical solution, so I can also execute, hey, I actually silently typed in analytical solution. So I'm going to give myself, I'm going to call it YA is analytical solution of X. Well, my analytical solution is 3. And for the last point, this one is 7, so I'm obviously pretty much off. This should improve for smaller h, but I'm gonna stop printing things because that's pretty primitive way to check things. It always works. Let's plot, okay? So let's plot. What do I need to plot these? Import matplot lib pyplot as plt. Then say plt xy plot xy. I love how I always have to execute things twice. Alright. This is my analytical solution, and the blue line is my solution that I got. It looks pretty similar to those on slides. So I'm far away because my h is 0.5. Let's try to improve. If I check for h is 0.25, and let me stop printing these values, I'm getting closer. If I put h 0.05, I'm getting even closer. Yes? That's the whole idea. You can go even closer. You can try pushing. Whoops. Whoa, that's nice. 0.01. You can keep going. This is computer. There we go. They're kind of on top of each other for 0.001. So this is the whole idea of doing a function. So function you can change. And you don't have to go to 4. You can go to 5. So let's go for a little longer. Okay? This is why it's beautiful to have a function that you can play with. All right. So did everybody get this? Should I stop for a second and get you a chance to?
Can you see how you graph it?
Hmm?
Can you see how your graph looks like?
This is for 0.001 on top of each other. If you want the back to that bad one, it's actually the same thing from the slides, by the way. It's just taken from a textbook. Okay.
What determines the largest value that h can be?
How much memory you have? The largest? Well, what do you mean by the largest? It's the
Like
entire
I
interval
increase
is
h
the
to be
largest.
above 1.
So if it's 0, 4, okay, if your interval that you're solving on is 0, 4, the largest h you can do is 4. End point minus starting point. But then you're just executing it once, and that's it. Yeah. And the error will be horrendous, okay? But that's what you asked for. Now, the smallest one, you can keep going smaller, but it's determined basically either by the machine epsilon or the memory on your computer. So whichever bites you first. Okay, so once again, I'm discretizing the space. So I'm asked to solve this on 0, 4. I have to give myself spacing h, and in this case, we said start with 0.5. So the points where I'm solving will be 0, 0.5, 1, 1.5, and so forth all the way to 4. If I give it a smaller spacing, then I'm going to have more points in between. And the more points I have, the finer will be my what we call resolution and solution. Right? So every time I'm looking for a numerical solution, I'm looking for a solution on a grid of points, and the smaller the spacing on that grid, the better. Okay. Now here the spacing is pretty large, and this method is pretty crude. So it's kind of the first and the simplest. First and the simplest is never the best one. Okay. So here I'm gonna just get, already in the first point, I'm pretty far away from what my analytical solution should be, right? And as I go, like, I keep kind of pretty far away from the points, but I'm still tracking the solution. I'm tracking the trend, if you will, of the function. And I can improve that by making this smaller. So if I put 0.1, I'm gonna improve the distance between the analytical solution and the numerical solution. Now, how do the mechanics of all of these methods is give yourself the space. So this is basically discretize your space, discretize the X space. So you always kind of start like that. And then reserve memory for y of x, right? And that's going to be an array corresponding to your X array. H, Xn, X0 are all the inputs that are determining your space where you're solving. Okay? And the only value that you give it that is related to the y is the initial point you're starting from. So I have to set that initial point, right? Set the initial value for y of x0, okay? And this is the length of the array, is n, because for the rest of these points, the way I set points y is that my y of I plus 1 is y of I plus f of x I y of I times x times h. And once I walk through them and set them, I'm essentially done. I return. For the remainder of this lecture, all we are going to do is we're going to try to improve on this, what I called slope. This was that dy dx, it was the slope. The crudest way to do it is that first order estimate of derivative. And basically improving the slope can improve my chances of being more accurate even for pretty large h. So the first way we're going to do that, so basically the code will remain the same except for this part that will change, and I might need to do some pre-computation to estimate this better. But the skeleton of the code will remain this, okay? And only in the case that I have an analytical solution, which I have in this case, I can actually compare to an analytical solution. Otherwise, I just kind of accept the method. I tested an analytical solution, and then for those cases where I don't have an analytical solution, I trust that the method works. But this is what gives me, comparison to analytical solution, gives me the idea how well does the method do. So let's try to improve this. So this is basically a range of solution. If I put all of those solutions on the same plot for 0.5, 0.1, 0.05, this is how you would basically approach this analytical solution better. And I plotted analytical solution for very fine resolution here, so it looks really smooth. Okay. So the first modification we can do is the following. If I did my method, Euler's method, it would take me, in this particular case, to this point, right? And I can see that I went kind of too far, so this slope was too steep. So one modification that I could do is like, okay, this is the point where this method would take me. I can estimate what the slope would be at that point and just average the two. Okay? So this point, this is basically the point that Euler method would estimate. I can find what is my slope is f of xy for that point. By dy dx is f of xy. So that slope is given by function f. So I can simply do that. Let's do that and see whether indeed we're better. So beauty of having a code already is that you can copy it, actually all of it. If your font is not too large, so you actually can, okay, I'm gonna copy part by part. Have to copy part by part. Alright. So I copied my code, and I'm just gonna rename this to this Hoynes method. So my Hoynes method says don't set this to the value. Basically, give it some, I'm gonna call this y0, not y0, y intermediate value. Is basically what I would have gotten with Euler's method. And then say that slope so basically I'm going to type this in. This is the value Euler method would give. Set as my next y. Okay? And then my slope will not be, it will be basically this previous slope plus f of at this new intermediate point and averaged. So just give me one moment to type this in. So what is this next point? What is its x on the slides? xi plus 1. And its y is this intermediate point that I computed. Temporary, however you want to call it. And I'm going to average these two slopes. This is the slope as per Euler's method, and this is the slope at this new point. And I'm just going to average them. And my new y is simply my old y plus this slope times h. This new slope. Yeah? So again, all of these methods, we're going to mention a couple of more, will be constructed that I'm like kind of trying to figure out the better slope. So next time we get to compare this to Euler's method. Yeah? Okay. See you on Wednesday.
So if you're doing something for homework, okay, enough time to do something now. If you didn't submit your homework,